To start with, let's now compare the reactivity of acid chlorides as an example of an acid halide with that of acid anhydrides in nucleophilic acyl substitution reactions. And again, the two issues that we should always be concerned with are electrophilicity of carbon of the carbonyl group and the leaving group ability. Let's now discuss electrophilicity of carbon of the carbonyl group. Well, Cl is an electronegative atom, so Cl pulls electrons toward itself in this CCl bond, leaving this carbon with a positive delta or a positive partial charge and a negative delta on chlorine or a negative partial charge. What about oxygen here? If you want to compare that with acid anhydrides, oxygen, of course, is also more electronegative than carbon, which leaves a positive delta on carbon and a negative delta on oxygen. But oxygen, as we have said before, we have mentioned before that oxygen has 2 lone pairs. So there are 2 lone pairs here. Now, because of that, oxygen can donate electrons by resonance. So we can actually do resonance here. So we can take that lone pair to make a double bond here, and of course, that carbon-oxygen bond is therefore broken. If we do that, then we get another resonance form here. Now, it's resonance donation, so there is withdrawal and resonance donation. So this is inductive withdrawal or withdrawal by inductive effect. There is also inductive withdrawal here, but also there is resonance. So there is resonance donation. Now, this donation of electrons reduces the electrophilicity of that carbon. If the electrophilicity of that carbon is reduced, then it is susceptibility to nucleophilic attack, and subsequent nucleophilic addition would be less, therefore. So this carbon, therefore, as a result, that carbon of acid anhydrides, as a result of this resonance donation, is less electrophilic. You can say it's more electron dense than that carbon of acid halide, so that's also correct. This carbon, therefore, is less electrophilic. Less electrophilic than that carbon because of this resonance donation. Now, so in terms of electrophilicity, therefore, acid halides are more electrophilic at this carbon, so that carbon is more electrophilic. So they should be in the nucleophilic addition step of nucleophilic acyl substitution reactions more reactive. They should be more reactive in that step alone. Now, the other issue that we always discuss is the leaving group ability. So the leaving group here would be Cl minus. Cl minus, and the leaving group of acid anhydrides would be the carboxylate. Now, Cl minus comes from HCl. We can look at the acidity of the HX or the halogen acid. Now, the pKa of HCl is -7. It's -7, an extremely strong halogen acid. The carboxylate comes from benzoic acids. Benzoic acids in general have a pKa of about 5 in general. So clearly, HCl is by far the stronger acid relative to carboxylic acids. Therefore, the conjugate base of HX or HCl in this case should be a much weaker base than the carboxylate ion. So this is a weaker base. This is obviously a stronger base, although it is stabilized by resonance, but it's a stronger base. If this is a weaker base, then this should be a more stable ion, and of course this would be less stable as a result, less stable ion. Weaker base, more stable ion makes this ion a very good leaving group, actually a better leaving group relative to the carboxylase. So this is therefore a better leaving group relative to the carboxylase. So in terms of the leaving group ability, the chloride ion is a better leaving group than the carboxylate ion. So not only that carbon in acid chlorides is more electrophilic than carbon in acid anhydrides, the chloride ion also is a better leaving group. So this entitles, if you like, acid chlorides to be more reactive than carboxylic acid anhydrides in nucleophilic acyl substitution reaction. So this is therefore more reactive in, of course, nucleophilic acyl substitution reactions, and again that's due to the higher electrophilicity of carbon of the carbonyl group and also the better leaving group ability.